Someone speak. I want to see if am I hearing you through the headset?
Hello.
Yeah, no, I'm not. Okay. All right, everyone. So we only have 2 topics left before we get into complete statics problems. And the topic today, which is looking at reactions at supports, is what you began on Friday in lab. So Rob was showing you a bunch of different connections and hoping that you would understand what we're talking about when we say reactions at supports. And then the second topic that we need to do is on Thursday, we're going to be doing distributed loads. So we have 2 topics, today's and Thursday's, and then we're set on having all the background to do every single type of statics problem from now on. Okay? So let me start out with just making sure that you're comfortable with the reactions at supports that you learned on Friday. And what I would like to do is I'm going to share my screen for a moment. Did you see this photo? Did he show you this sketch on Friday? He might have had his own version of it. It's looking at all different kinds of connections.
I think they were all chopped up. I think we saw the pictures separately on the worksheet we did.
Okay. So the second sheet here is all 3-dimensional connections. And this first sheet is 2-dimensional connections. So let me just start by just showing you what he was explaining to you. So this right here is a pin. There is a rod here that's connected with a pulley, and it's connected by a pin. Can everybody see that? We're considering this a 2-dimensional object. So if we're considering it 2-dimensional, let's start with Amani. If we're considering it 2-dimensional, what kind of motion can these 2 objects have relative to each other?
They can have a rotational motion.
Okay, they could have a rotational motion about z, right?
Yeah.
We're going to assume on all these 2D problems, this is my x and this is my y. So it could have a rotational motion about z. Okay, how about Angel? What other kind of motion can this pin, can this pulley and this rod have in relationship to each other that the pin might be preventing, since it's 2D?
There could be some sort of translational force.
There could be a translational motion in the x.
Yeah.
And there could be a translational motion in the y. So there are 3 different types of motion that a 2-dimensional connection can withstand. One is a translational motion, let's just say a force in the x, a translational motion in the y, and a rotational motion about the z. So looking at this pin, which is connected right now, connecting these 2 objects, Bon, can these 2 objects, I'm pushing it in this direction, can these 2 objects resist a force in the x?
Yeah, because it's pinned down.
Because it's pinned down. How about, Bon, keep going. How about, can it resist a force in the y?
Yeah, for the same reason.
For the same reason. How about a moment? Can it resist a rotation?
No, it's gonna spin around.
Right. So a 2-dimensional object has at most 3 motions it could have. A movement in the x, a movement in linear in the x, linear in the y, and a rotational about the z. When we look at the pin connection, a pin connection resists a translational motion in the x. It resists a translational motion in the y, but it can spin. So the reactions at a pin support is a force in the x and a force in the y. And the reason why, because this can't move in the x and it can't move in the Y, if I apply too large a load, I could break the pin in this direction. I could break the pin in that direction. So it's important for me as an engineer to understand, based on all the forces in the problem, what kind of force in the X and the force in the Y must this pin be able to withstand? Okay, so the term reactions it supports means the motions that it can resist. So now all of you have a ball and socket joint in your arm. So I'm up to Colin. A ball and socket joint, we're considering a three-dimensional object. So what are the possible motions that a three-dimensional object can have? We know on a 2D, the possible motion is translational in X, translational in Y, and moment and a rotation about the Z. What about a three-dimensional object, Colin? Okay, maybe not here. Daniel C. Okay, Daniel Hall. Boy, I'm flying through the list. Danny.
Yeah.
Great. So a three-dimensional object, what's the possible motions a three-dimensional object can have?
It would be translational in the X, Y, and Z.
Great.
And then moments along the X, Y, and Z.
And then rotation in the X, Y, or Z. So there's a maximum amount of six motions that a three-dimensional object can have. So let's think about your arm right now. Your arm is connected to your shoulder by a ball and socket joint, assuming you have no injuries. Can a ball and socket joint prevent translational motion? Can I separate my arm from my shoulder in the X, Y, and Z? Linear motion. Yes, I can. How about rotation? Can I rotate in the X, Y, and Z?
Wait. You can't separate your arm from your shoulder.
Right, I said, didn't you say no? You can't.
Oh, no,
so it can resist
yes,
it.
I can. Okay, never mind.
Okay, no, I can't separate my arm from my shoulder. So that means it resists a force in the X, Y, and Z. Translational motion in the X, Y, or Z. Okay, sorry if that confused you. What about rotation? Can the arm rotate from the shoulder in the X, Y, or Z, Danny? Danny, you still here? Or did you leave?
Oh, no. Sorry.
Danny, can you rotate your arm relative to your shoulder in the X, Y, or Z?
It's X.
Stick your arm out and spin it.
And in the Z it goes. Rotate them on the Y, no. And you can only do it slightly in the X, right?
No, a ball and socket joint. What's up with your arm? Look at my arm. I could totally spin it in the X.
Okay.
I could totally spin it in the Y.
I was just keeping
I could totally spin it in the Z.
I see.
Right?
Yeah.
Okay. All right. So that means a ball and socket joint can only resist translational motion in the X, Y, or Z. So that means as an engineer, when I'm designing with a ball and socket joint, I have to find what force in the X, what force in the Y, and what force in the Z it could withstand, and then choose a ball and socket joint based on that. Now, I'm going to stop sharing for a moment. That was supposedly review. Did you guys get this on Friday? That for 2D objects, there are three possible motions: translational in the X, translational in the Y, rotation about the Z. And in the 3D object, there are six possible motions: 3 translational and 3 rotational. Okay? And what you're trying to figure out is what can each of these connections resist? Meaning, the two objects that are connected together, can they move relative to each other in one direction? Can they resist a rotation? Okay? So when you filled out that table, this table, this is the table you had, right? You guys? So a pin is a 2D object. It has nothing to do with force in the Z or moment in the X or Y. These are the only three, Fx, Fy, and moment Z are the only possible things it could resist. And remember, look at the column. The title of the column says forces and moment it resists. So a pin, as Bon explained, it could resist in a force in the X and it could resist a force in the Y. So the reactions at the supports are a force in the X and Y. Let's go down to a ball and socket joint. It's a 3D problem. So it could possibly resist all 6 of these motions. But we learned that a ball and socket joint can rotate relative to each other in X, Y, or Z. So the only thing it could resist is the forces in the 3 directions. Okay? Think of a door hinge. Actually, let me go to the other picture. Can you see the schematics here in front of you? You guys?
Yes.
Is this
Yeah.
Is this kind of like an application of like equal and opposite reaction sort of deal?
It will be once we put it all together.
Okay.
Okay.
Is that why the book likes to say force couple? Because if you have like a force and a connection, the connection basically creates a couple instead of force moment.
No, the reason they use the word couple for moment is that 2 forces that are a couple create a moment. It has nothing to do with the connections.
But is that always true?
What?
What if they're concurrent?
Good point. Okay, no. You're right. Great point. So the textbook likes to use couples, but it has nothing to do with connections. Okay, let's go to a hinge. And a lot of these you could play with, you have in your house. You have a hinge on the door. I happen to have a hinge right here. I have 2 pieces that are connected by a hinge. It's a 3D problem. So let's think about it. On a hinge, are these 2 objects, can they resist a force in the X, a force in the Y, and a force in the Z? Yeah. I can't move these 2 pieces that are hinged together relative to each other in for translational motion. What about a rotation? Certainly these 2 pieces can rotate about each other along the axis of the hinge, but otherwise they cannot rotate in that direction and they can't rotate in this direction. So if you look at the reactions of a support on a hinge, you see there's a Rx, Ry, and Rz representing the forces, the translational motion that it could resist. And then it also has a rotation about the X and a rotation about the Z, because that is preventing motion in that direction. However, around the Y, these 2 pieces can rotate via each other. Okay, so this 5-minute review turned out to be a 15-minute review. Okay, and so you want to go through all these connections and make sure that you're comfortable. Make sure that you're comfortable understanding the connection. You never want to memorize things. So what I'd like to do now is go forward on what our topic today is, to draw free body diagrams of rigid bodies with connections in them. And then if you're finding you're getting it really quickly, we could go back and review more of these connections if we want. And it'll basically be a function of what you guys want to do. Okay. So.
Jen, can I ask a clarifying question?
Yeah.
Before we move on.
Yeah.
I think what's confusing, at least for me when we started doing this, is that the vocabulary feels kind of backwards, right? That hinge, for example, you're saying it has this motion, this twist, this twist. But
Correct.
We're talking about the ones it can't do. We're talking about the ones that it restricts rather than the ones that it allows. Correct. And I guess the reason we do it that way is because we're going to be talking about the ones it resists, right?
Correct.
Okay. Because like that,
really great.
That picture, yes. It seems confusing, right? It's not rotating around the one that it can rotate on.
Correct. So these are called, let's see, does this work? Okay, where is, I have to pull it up as a PDF. Hang on a sec. Could you just explain that again, David, while I'm doing this? Clarifying it rather than
Yeah.
problem.
So what was tricky for me is that the ones we are considering are the ones that the physical object can't do, the ones that it resists. So
That's correct. That's correct.
And I think the reason, like Rob called them unknowns, because in the future we're going to be solving statics problems where the ones that it resists are the ones that we need to talk about. The ones where it stops the motion are the ones that we have to account for. Is that right?
That's correct.
Okay.
Okay, could I draw on it? Why on it? Okay, you guys. I had this already last night. Okay, I have a file open. I want to open it up as a I'm going to stop sharing for a minute. Yes. Okay, I got it. So let me just explain that again. When we look at a hinge, we're trying to figure out how it could possibly break. Because as an engineer, we have to design it so it doesn't break. So we need to be able to calculate the values that it can resist, because it will never break by spinning in the Y. If you only rotate it in the Y, it won't break. So in the pin connection, with the pin, I could spin a pinwheel as much as I want, and I will never break it if the only loading that it's experiencing is rotation. But if I start pulling on that sucker, I could break it because I could break the pin. So reactions at supports are the items that it can resist because we need to calculate what they are. If a pin has a load of 10 pounds going up and 10 pounds going to the right, the resultant of that is what, 14.1, I believe? 14 pounds. I need to make sure that I pick a pin that can handle more than 14 pounds so it doesn't break. Does that make more sense now? Okay, so the reactions of the supports are the motions that it's prevented from doing, and I have to calculate them to be able to make sure that I'm designing it not to break. Okay, I'm going back to, okay, so where I'm going now is back to our modules. Can you see my screen? You see the modules or no?
We still see the pictures.
You still see the
force
picture,
pictures,
okay.
the connection pictures, yeah.
So let me stop sharing and let me share. Okay, now you can see the module, right? Tuesday, October 13th, we're doing free body diagrams of rigid bodies with reactions at supports. So here were the reactions at the supports, the table that I picked up already that you saw that has all the reactions at the supports shown. This is the table that you worked on it Friday and it's completed. And now what I want to do is I want to open up this because we're going to start doing all these free body diagrams. Okay. Still not showing as a PDF. Hang on a second. I'm going to go out for a minute. If you guys want to help me, obviously I just did it once and now I can't remember. When I'm trying to open up a file, but I want to open it up as a PDF. And what it's doing is it's keep opening it up as a web document.
So Joanne, it's opening as a PDF, but it's doing it in Firefox or whatever
So
you're
how
in.
do I get it out of Firefox?
So go back to your downloads, click on the downloads up top right. Yep, and then open that. Yeah, go ahead and like right click on that and hit open with another, open with, and then open it.
Right click here.
On the free body diagram with connections, the name for that. Or if you open that file, that'll work too. You just don't want to, don't left click on it, right click on it and hit open with, and then go and hit it open with Adobe.
Okay, let's try this again. How about this? Alternate formats.
Joanne, it's in PDF already. If you download that one again. And then, okay, so instead of open with Firefox, there you go. Hit open with, and then
It's not letting me pick PDF.
hit other. And then you'll have to select, there you go.
Okay. Sorry, you guys. All right, what do you see?
We still see the Canvas browser.
Okay.
If you successfully opened it in Acrobat, you just need to share the Acrobat window.
Yeah, but I wasn't able to. It's now giving me a response of I have to say sign up for 7 days.
Oh boy.
Okay, I guess we're doing it by hand.
What do you usually open it in, Joanne, on the PDFs?
I usually use the other laptop I have. I don't use this one as often. So it may be that.
Is the problem that you have to write on it? Is that
I was going to try to write on it because I know
I got you.
kind of what you guys
go to your
prefer.
downloads, if you go to your downloads folder, just the folder, and click on the file from there, it might open it in PDF.
Yeah, no, it's not. All right, I'm going to just go on to my other laptop. All right, sorry, you guys. Okay, so I'm doing it by hand. Okay, so what we're doing right now is we're going to be drawing, and let me get a marker. Okay, so we are going through about 30 free body diagrams. And this is basically your homework. They're all short, small free body diagrams. But we're going to be going through as many as we can in class, and then the rest you'll need to do for homework. If you want at the end, I could tape something, or right now it's 10 o'clock and at 10:30 you're taking a quiz. So we're going to go one at a time. So, and what I'm going to have handy, in addition, to having this, since we're just getting comfortable with reactions at supports, I'm also going to have this cheat sheet that I already filled out in lab. But it's more important to understand what something is resisting than having something on a cheat sheet. So let's take a look at what's going on here. So we're going to start with number 1. Can everybody see what I have here?
Joanne, I have a question.
Yeah.
Since we're going to be submitting this, would you want us to be doing this in engineering paper?
Yeah. Right now I'm just doing it on scrap right on the sheet. But then you're going to just watch what I'm doing.
Definitely. All right.
Okay. All right. So in this case, we have the idea, the question says to draw free body diagrams of all the members. And only if they put a little G here do you include the weight. Otherwise, you ignore weight. Many times in statics, when we do analysis, we ignore weight. So we have a beam here, and we see that it has an external load at P. So we're comfortable with that. And we know there would be a weight here. So let me zoom in right now. What kind of connection is this? It looks like this wall, this beam is embedded in the wall. What's the name of that connection?
Fixed.
Am I gonna, it's a fixed support. If it's embedded in the wall, am I gonna go through names? Let's go through names. So I'm up to Dave. Dave, if it's a fixed support, even if you didn't know the name of this fixed support, we're looking at a wall connected to a beam. Can it move in the X direction relative to each other?
No, a fixed support will resist all three motions in 2D.
Great. So it's going to resist a force in the X, it's going to resist a force in the Y, and it's going to resist a moment in the Z. And let's call this point A. So I'll say force AX, force AY, and moment A, and it's in the Z. So what I'm drawing is I'm drawing the reactions at that fixed support. It's a two-dimensional problem. It at most could resist 3 different motions: translational in the X, translational in the Y, and rotation about the Z. So my free body diagram then would be this object. I would have its weight going down. So this right here is scrap. I would have the P here. I would have a force in the X, force in the Y, and a moment about the Z. And had this had distances, I would have had distances on here too, because a free body diagram now of a body has to have the distances and also has to have our axes.
So
Dave?
now I'm confused about notation, because before we were calling them something else. It was like Rx for resistance X and R for reaction, right? But now you're putting Fs. So I guess I just want to clarify how we're the vocabulary for that stuff, like how we're
Okay.
Great question.
notating.
So did Rob talk about R's? Where
Yeah,
did you
he
get
used
R's?
reaction, as Dave is saying.
Okay.
Yeah, he would use an R for if it was resisting
R.
that motion.
Okay, so there are going to be problems where you'll have 3 connections on a bar. So we could call them RA, RB, RC, but we've used R as resultants in the past, right? What I tend to do, instead of using F, because when we do some of the forces, we're going to use F anyway, let's just call this AY and AX.
Okay, Joanne, I just want to clarify. So basically, in this free body diagram, we're drawing those are the forces from the connection on the beam, right?
That's correct. Because
Okay.
remember when we had a cylinder on a surface, right? We knew there was a normal between here. When we separated the cylinder from the surface, we had to account for that. We had to put the normal in. We had a weight in. And if there was a tension, when we cut the tension, we put T for tension. Now what we're doing is we're removing the beam from its fixed support, and we have to account for that motion, that movement away, right? So there is internal to the system, there is a force in the X that's equal and opposite. There's a force in the Y that's equal and opposite. And there's a moment equal and opposite in here. So when I remove the beam from the fixed support, I have to denote those, I have to put those 2 forces and the moment in.
And to
Wouldn't the
follow up on
moment
that,
be the other way around? Sorry.
Good
Yeah,
point.
I'm trying to figure out directions,
Yeah.
especially AX as well. Like
Okay.
would it be pulling? I don't
Good.
know.
It doesn't matter how it's drawn, because in the end, when you do your equilibrium diagrams, what will you get if you drew it in the wrong direction?
A negative.
A negative. So this is not a complicated problem yet. And because it's not a complicated problem, you're wondering, well, I kind of know that it's going to be in the other direction, and don't worry about it. We're going to get to a problem like this, where we have a journal bearing, a ball bearing, you have two normals, you're going to have a ton of forces on here. So what we tend to do is always draw it positive. And then if we get a negative, we know it's going in the other direction.
And so we draw in all of those reactions just as stand-ins, even if, like, as you're saying, because this is relatively simple, we can see there's no like X force.
That's right. When you go to do the sum of the forces in the X later, you're going to find that AX is 0, right?
Okay.
But you
Gotcha.
have to draw it because a fixed support can withstand an AX. And then you have to do the equilibrium diagram, equilibrium equations, or you could say AX equals 0, but you have to draw all the possible reactions at the supports at each support. Okay, so to go back to Dave's question, you could choose whatever variables you want. I tend to draw, knowing what the point is, I tend to write AX and AY because I may have an AX and AY, a BX and BY, a CX and CY, a DX and DY. I may have a ton of them. So I don't want to have all these subscripts. So I wouldn't use F and I wouldn't use R. But for each one, when he introduced them to you, he used R because there was only one support that you were looking at for each of the reactions at that support.
Yeah, okay. I guess A makes sense because we're talking about the connection at A, right?
Great.
So
let's use AX and AY. Okay, David LR. Let's go to the next one. So again, we have a beam. So if I draw my beam, I have A, B, here's the middle, and I want to start, even though they should have.
Scroll down, please.
What?
Please scroll down.
I didn't hear. Oh, scroll down.
I cannot see what you're drawing. Yes.
Thank you.
There we go.
Okay, so David LR. So I'm drawing my beam, and they should have given us distances because we have to have distances on free body diagrams, and we also have to have an axis. So David, from this information here that's given, what forces should I draw on this?
You should draw force P.
Great. So I have force P. What else?
The weight.
The weight. What else? What's going on at B?
There's a normal.
A normal. And since there's only one normal, you guys, problems are going to start getting more complicated. Since there's only one normal and one weight, just call it N and W. Don't put any subscripts. And then this distance here is 45 degrees. Okay, what else? What is going on at point A? What kind of support is that?
It's a pin.
A pin. And what could a pin resist?
X and Y, but no
Right.
moment. B.
AX, AY. That's it. So instead of drawing free body diagrams of points, we're now drawing free body diagrams of rigid bodies. We have to account for all the loads on it, including the reactions at the supports.
So I have a question forming here.
Yeah.
Okay. So I would think that there are two normals. I would look at this and think that there are two normals that are contributing to keeping that bar.
Do you mean at B?
Going anywhere. What?
Do you mean at B?
So there's one at B and then there's one at A.
Okay, so what's happening now is you're correct. You could say maybe that this is a normal because it's actually they're pressing against each other, so there is compression, but it's standard to just call it AX and AY.
Because
in the end, you're going to find what force is actually in there, and you'll find the direction. So look, right now we have two weights going down, and we have a normal going up.
Yeah,
right?
like if
I'm
that
sorry, we have a
45
weight and a P going down. So AY is probably going up and AX is going that way. So really, if this is truly the direction, the resultant of these two forces is really a normal.
Yeah.
Okay?
Yeah, that's what I'm talking about. So, I mean, the way that we draw these free body diagrams is contextualized, must be contextualized by what the question is. So in this particular context, it's not just a free body diagram in the situation. It's like we're studying that pin connection.
We are drawing up till now in, hang on.
Otherwise, we might choose to put a second normal instead of the AY-AX.
Right, so hang on.
But if you think about the problem that we did for the interview, how there were certain normals in that problem where we knew it was normal, but we didn't know exactly in what direction, and it helped to be like normal X, normal Y. I feel like for supports, it might be the same. Like, yeah, you know there's a normal there, but you don't know in what direction it's going to be. So it helps to just put like a reaction in the X and a reaction in the Y.
I think we all got different interview problems.
Oh.
Yeah, but you all had different ones, but okay. Maria, thanks for that explanation. And then I'm thinking, I'm not quite sure what Jason's question is, but let me answer it this way. All the problems we've been doing the last couple of weeks about moments, we've been ignoring the connections, right? Remember that couple problem we did where there were two pin connections? It was a pin and a roller, and we totally ignored it, right? Let me pull up the problem. Remember this problem? And actually, when you guys looked at it, the first thing you guys looked at these 2 points where it's connected. And I said, we're ignoring that. We're not looking at that. Right now, we're learning about couples. We learned the total, what was going on in the system, right? Now what we're doing is we're now saying, okay, I'm now throwing in the connections because these two connections have to resist all those moments that are created by these couples. So in the last 2 or 3 weeks, we've been ignoring all connections because we have only been looking at figuring out moments. Now we are looking at the complete free body diagrams and looking at all the forces on the system, including the reactions at the supports. Let me go on to another one. So we are at Edgar. Yes. So there's a bar here. And if I were to draw a free body diagram of this bar.
Can you move the page a little bit down?
Yeah.
Thank you.
Yeah. Okay, remember you guys, these are free body diagrams. You have to have an axis and you have to show distances. So just call them whatever you want because they're not giving you distances. But I don't want them to screw you up. You have to draw distances of the bar. We're drawing free body diagrams of bodies. We need to know what their dimensions are. Okay, Edgar, what forces should I draw on this free body diagram?
We have force P.
Okay, we have P. What else?
We have a tension.
We have a tension, and
point B.
Stupidly, they don't give us what the angle is, but I'll just write it's alpha. And then what do we have going on at A?
Is that a bracket and a pin?
It's a pin, correct.
Okay.
So what does a pin resist?
It resists motion in the X and Y.
Right, so I'll call it AX and AY. Okay, for some reason it seemed complicated when we started this topic, but I'm hoping it's not complicated. Maybe sometimes I just don't explain things well. Okay, let's go to a more complicated one. So far we've seen a fixed support that resists two forces in a moment. We've seen pins that resist a force, two forces in an X and Y. Let's look at another one. How about this one? Let's look at the guy who's jumping off a diving board. We're up to Elizabeth. You here? Eric.
Good morning.
Good morning. So Eric, we're putting A, B, C, and whatever those distances happen to be, distance 1 and distance 2. And we need to make sure that we have axes, right? So
Yes.
two things always to remember when you're drawing these. Two, draw the XY, draw the axes and put in some arbitrary distances, D1, D2. Okay, so Eric, what are some forces on the system?
We have the weight of the diver at C.
Great, and I'm just gonna call it W because there's only one weight. What else?
I'm looking at A and I can't really tell what kind of
Okay,
connection
let's zoom in a little bit. Look at, you could see a little, I don't know if you could see it on your copy, but there is a little difference between A and B.
Yeah, it looks like B's not actually connected to the diving board. It's kind of resting on top of it.
Correct. So what kind of force would that be then?
That's just the compression force. I don't know what to call it.
Oh, it's
though.
resting. When things touch each other, what's it called?
I don't know.
Normal,
Normal.
right? Normal.
Yeah.
Okay, so whenever you touch something, think it's a normal.
Okay, and then
Okay.
it looks like a pin at A.
It's a pin. So what do I draw?
X, X or AX, and then
AY. There was something that I was impressing upon you when we were drawing free body diagrams before, and it might be more clear now. Notice I am only drawing a free body. Free means it's not connected to anybody. It's free, it's on its own. I'm just drawing the bar, in this case, a diving board. I'm removing it from all its supports, and I'm only drawing forces on it.
Joanne?
Yes.
So
Amani.
I thought we were only taking the weight when there's a little G.
Yeah, but they're talking about the weight of the body. So there's a little G here because they want you to include the weight of the beam. Here, the diving board is negligible. So you don't use the weight of that, but you still have to account for the external load of the weight of the person on it.
Okay, thank you.
Good question. And the reason why in statics many times we ignore the weight is because the weight is so light in comparison to other things. Okay? All right, let's pick another one.
Quick question about that last one.
Yeah.
What was the connection furthest to the left at A?
This is a pin.
Oh, okay.
It's a pin connection.
Gotcha. So
okay, you're looking through a document camera at a photocopy.
Yeah.
You know, we were supposed to look at the original, but I'm not good at that. Okay, how about let's do this. Let's do this one. So we're up to Gerardo. They're asking us to draw a free body diagram of both those objects.
I'll pass.
Okay. Hyoji?
Yes.
So we have A, B, and C. And then we have D, E, some point that they're not calling anything, and F. I'm drawing my axis. I'm drawing my axis, X and Y. It's giving me it's at a 3. That's interesting. 3, 5 something triangle, not 3, 4, 5. Okay, Hyoji, looking at A, B, and C, what forces are on this A, B, and C bar? Can do it. Should I zoom in? What's happening at A? What does it look like?
Is it connected?
It's connected, but can you tell what it is? It's a rope. So what force do I put? Yoji, I'm going to have you pass, okay? Isaac? What do I have at A? I have a tension. What's going on at B, Isaac?
We are going to have a resistance in the X and Y that looks like a pin. So
it's a pin. BX, BY. And again, notice I'm always drawing them in positive, right? Okay, what's happening at C, Isaac?
At C, a normal. Well,
right.
We could call it force from D because it's.
Nope, we're calling it normal. I don't want to put any F's in here because I'm going to have to do some of the forces in the F later. It's a normal. It's a normal between C and D.
Is it?
Yeah.
Is it a normal how you drew it, like at that angle? Or would it
yeah,
be?
because it's touching right here. It's horizontal.
Okay.
I guess if we I guess because she said assume everything's smooth, then it
right.
would be, if there was friction, there would be downforce as
right,
well.
but we have no friction yet. Okay. Okay, Isaac. Jack.
Hello.
Hi. Okay, so now we're doing DEF. What do I have to do at D?
I can't tell, but I think the only contact is just on C. So
correct. Yeah. The only thing that's happening at D and C is that they're touching each other. So on body ABC, I drew the normal from D going to the left. So what do I need to do at point D?
Draw the normal coming from the left.
Right. It's equal and opposite, right? Okay, what's going on at E, Jack? Can you see?
I see some things there.
Okay, take a guess at what do you think it is? The most common connection in the world.
I think it's fixed, but I can't tell.
No, it's a pin.
It looks like a pin, but I don't understand how that pin would work in this situation.
In this, well, it's a pin. Basically, you look at the picture and you determine what the connection is. And if we were building it and we were outside our engineering lab and we wound up building it, we would get a pin and we'd shove it in. Okay? It's a pin. So what does a pin resist, Jack?
It resists all the, it resists the forces in the X and the Y.
Great. So since it's at E, I'll call it EX and EY. And notice again, I'm always drawing it positive. Let me zoom out now. Now, Jack, the fixed support that you saw, and everybody, if you want to look, the fixed support is up here. That's where the shading is, right?
Oh, okay, yeah.
Right? Where this bar is connecting, this little connection here, this piece, that's a pin. and I'm analyzing bar DEF. I'm not analyzing this little piece that's coming out. Jack, keep going. What else is going on here?
At E?
No, on the bar, DEF.
At F, there's the weight of the weight.
You have the weight at F. And I should put in my distances, distance 1, distance 2, distance 3, distance 4, distance 5. And then there's one more thing, Jack. What else is on here?
It looks like there's some kind of moment.
There's a moment, correct.
In between.
Just like there's concentrated forces at times, this is a concentrated moment, and they're calling it M, and it's in the positive direction. It's being placed right at this dot. And Jack, knowing that this is a two-dimensional problem, what is that spin going around?
The Z.
The Z direction. So we have two free body diagrams here. Okay, I'm going to stop for a moment. And so right now it's 10:30, and ordinarily you would take your quiz. And my suggestion is that we keep going on this, and then you take the quiz outside of class. Is that okay with you? Okay. Okay. So we're up to Jason, the void.
Can we do one with a cylinder?
Yeah. I want to continue looking at this problem though. I want to know now, what if I wanted you to draw a free body diagram of bar ABC and DEF together? So here's A, B, C, D, E, F. So Jason, if I wanted you to draw a free body diagram of both bars together, what would you draw on it?
It's the same thing, except the normal forces are internal.
Great, so just walk me through.
Well, you've still got the tension going left at A. You've got the pin joint, which is comprised of BY and BX going up and to the right. And then you have EY and EX at the other pin joint going up and to the right. And then you have the screwdriver moment, concentrated moment, yeah, and then weight going down at F.
Great. Now, you can see how these free body diagrams could get kind of complicated. It's better to draw them big. Okay, so all the forces that were external to both these bars are also external to the bars together, with the exception of the normal. Because once bars A, C, and DF are still touching, that normal force is internal to the system, and you don't draw it in the free body diagram. Okay, what's missing from this free body diagram? I forgot to draw the axes, and I forgot to put all the distances. Okay, let's go to another one. So, so I think it was Isaac asked for a cylinder. So let's do this one. And we're up to Jason Lee.
Yes.
So let's put the stuff on scrap first. Okay. So what's going on here, Jason? What do you see?
We have pinned down L-shaped container thingy.
Okay, so there's a pin. Tell me the point it's at.
It's at A.
Okay,
and
so I
we're
have to
going.
have an AX and an AY, right?
Yes.
The pin.
And
Okay,
then we have a normal touching at B.
I have a normal at B. And in this case, I'm going to call it NB.
Yes. And
What else do I
we
have
have
in
a
here?
normal between the first cylinder with the wall.
Okay, so let's call this, you know what? Looking at this, I might actually rotate my axes. Nah, we'll just keep it this way for now. Let me draw it with a different color. So we have a normal coming in here, right? Let's call it normal 1. There's also a normal 2 here, right?
Yes.
A normal 3. And then there's a
Something in
normal
between.
between the cylinders. Let's call it N sub S, a C for cylinder. Right?
John, I have a
Dave?
question.
Yeah.
Okay, at B, that's a connection, right? That's a roller, which we've talked about.
Right.
Do we need to call it as such, where it's a
You can
reaction of roller at B, or is it okay to call it whatever?
Just call it whatever you want. Just call it a normal.
Okay.
Yeah.
What? I mean, so how do you know when to prioritize like multiple connections as?
These are all forces that are present on a body, whether it's a normal, a tension, me standing on it, Laura pulling it, or pins. They're all forces that are acting on a body, right? So we were already comfortable with normals, so we don't have to say it's a reaction at a support. But if you have a roller, that's touching the surface, it could roll, it could rotate, it's free to move in this direction. It's free to slide this way. It's free to rotate. The only thing it can't do is the force in the Y. So you could consider it a reaction at a support, or you could just say it's a normal.
There are 3 different types of connections that only have one resistance. Are they all going to be like that?
Yes, they're all in the same category. Roller, rocker, what are they all called? Let's find them. Here they are.
Well, I mean, like collar on smooth shaft is only
yeah.
1, and pin in smooth guide is only 1.
Right, correct. But let's just look at this one for now. Right here, there's a ball, a roller, a rocker. Basically, in the end, yes, the textbook calls it R, but I would just call it a normal. You could call it R if you want, but it's really just a normal. This thing is only just touching the surface. It's a normal. I'm sorry that things are being created, confusion is being created.
I feel like that's different, but maybe that can be a question for later. We can move on, sorry.
Okay. But if we want to look at some of these collars in a smooth shaft, do we want to look at those?
No, I think my question is theoretical about how we're going to treat that stuff, so we can keep going. I'll ask later.
All right. So let's look at this. What Jason just identified is that there's a normal between this bracket and the cylinder, the left cylinder. There's a contact surface between the bracket and the left cylinder. There's a contact surface between the 2 cylinders. There's a contact surface between the bracket and the cylinder. There's a pin connection, and then there's a roller over here that creates a normal. So now the question is, well, what do we want to draw a free body diagram of? So let's draw a free body diagram of free body diagram. Looks like a smiley face. Let's draw a free body diagram of this. So I am on Jordan. Jordan, for the bracket, if I'm just drawing a free body diagram of the bracket, what do I draw? Earphones. I mean, you're on mute.
The pin, which is AY,
pin.
AX.
Great. AY,
And
AX.
the normal forces and the angle.
Right? The normal coming down here, which is normal 1. The normal coming down here, which is normal 2. The normal coming down here, which is normal 3. And then I have that here.
Yeah, that's it.
Good. So everybody, look at this bracket and look at all the forces that are put on it. The cylinder's creating a normal. The cylinder's creating another normal. The pin is creating 2 reactions at the supports, AX and AY. This cylinder is creating a normal, and then this connection here is creating a normal. Here is my free body diagram of the bracket. Any questions on the free body diagram of the bracket? Okay, Jordan, keep going. What about now if I draw this left cylinder?
That has 3 normal forces on it.
Normal 1, normal 2, and we called it normal C, right? The cylinders. And, you know, had there been a weight, had they told us there was a weight of the cylinders, I would have had a weight on here too, right? And Jordan, you want to do the last cylinder?
That has 2 normals on it.
Okay, hang on a second. Normal 3 and normal C. Okay, who just talked? Isaac, was that you?
Yeah, is proper convention for drawing these normal forces to draw them as a compression, or you're kind of drawing them through the bar, or does that not really matter?
It doesn't matter, because some of you, you know, I probably, if I was neater, I would have drawn it like this, right? But some of you like to draw them out here. It doesn't matter. The point is that it's along that part.
Gotcha, thank you.
Okay, can you, Jordan, can you tell why I'm enforcing that we put distances on here? Why do you think we need those distances? Thinking ahead.
I assume they'll matter when we're calculating everything.
Yeah, when we do some of the moments about points, I'm going to need those distances to those forces. Okay. You know, let's see who's next. Cody. Okay, Laura.
Yeah.
Take a look at this. This is really important, you guys, because it's going to simplify your problems. If I choose the axis like this, are any of the ends going to fall on that axis?
No.
Which is going to be a big old pain in the ass, because I'm going to have to get components of every single end. So what do I want to do instead, Laura?
You want to rotate your axes at 30 degrees?
Yeah, watch this, you guys. I'm rotating my axis, and now I'm deciding that I don't want my AX and AY to be that way. I want to put my AY and my AX along the axes. Because I want to simplify the math. It doesn't matter how I put AY and AX, because when I get the values of it, I'm going to know what directions they're going in. Is everybody comfortable with that? Did I just confuse people? Rotate your axis to simplify the amount of math you have to do. So put your AX and AY along the axes that you're choosing. Okay, so now let's draw a free body diagram. So now let's draw a free body diagram like this. So Liam,
Yes.
when the free body diagram, when I'm drawing a free body diagram of the two cylinders and the bracket together, what forces do I draw on it now?
The AX, AY, and NB.
AX, AY, oh, and we decided we wanted to do AX like this, right?
Whoa, I haven't seen whiteout in like 20 years.
Yeah, old school.
Those correction tape things, I don't know if it's because it's designed for a righty. I mean, I don't have any problems with anything else in terms of being lefty, but for some reason it doesn't work for me. It could be impatience, or maybe I'll blame it on being lefty. All right, so let's see. The normals all cancel, and I only have AX, AY, and NB. Are you getting more comfortable with free body diagrams? Free body diagrams.
Yeah.
Okay, that's why we're going to do so many of these. That's why you have 30 to do.
As far as this question was concerned, like as a homework question, it would only want us to draw the bracket, correct?
The problem asks to only draw the bracket, correct? Yes, you would only draw out of the bracket.
For this last one, do we need to include distances?
Say it again?
For this last one, do we need to include distances?
Yeah, we should always have distances. Always have distances, because the next step you would do is do sum of the moments. And in order to do sum of moments, you need distances. Okay, let's do a little bit more challenging one. Did you guys get an understanding of what journal bearings are and thrust bearings? Did you guys get a feel for those?
We talked about them, yeah.
So let me just mention them. You guys, basically you have a rod and a collar, and it's called a journal bearing. You have to memorize the name. Journal bearing is a rod within a collar. Here it is. Here's a rod, and it's inside a collar. It could move freely in this direction relative to each other, so it does not resist a force this way, but it does resist a force perpendicular in this direction and perpendicular up. Perpendicular to the rod in both other directions. It also can't spin around those axes, but it can spin around this axis. It's spinning right now. So a journal bearing can resist a force going this way, a spin this way, a force going this way, and a spin going that way. That's what a journal bearing is. A thrust bearing is a journal bearing with collars on it that you could tighten. So it has a collar that I slip on here, and I slip it on here, and I tighten the collar so that this cannot slide anymore. So the difference between the journal bearing and the thrust bearing is the thrust bearing has these two pieces here that prevent now movement in this direction, so there's an extra reaction at the support. Okay. The next one is a ball bearing, which is probably the most confusing. here's a ball bearing. Okay, everyone, it's a journal bearing again. It's a rod in here. If you look close at the collar, you see that there's this metal piece in here. If I could pop out that metal piece and instead put a center of ball bearings in there, it would allow my rod to rotate, to tip. So instead of having this piece in here that restricts the rotation, there's a series of ball bearings, see it's right here, around this outside that allows this now to rotate in both directions. So you start out with a journal bearing that what it can resist are two forces and moments around the same axis. You take a journal bearing and you put collars and lock them on the sides, and now it prevents motion, translational motion along the rod. So it adds a reaction at the support. A ball bearing is a journal bearing that puts a row of balls in here that allows some rotation. Okay? All right, so those are important for us to know. So let's take a look at this problem right here. It says the bent bar show. So they want you to draw a free body diagram of this bent bar. The support at A is a journal bearing. Okay? Journal bearing is that first one. So where are we? Luis. Luis. Okay. Mackenzie.
Yeah, what's the question?
Okay. This is they're telling us this is a journal bearing at A. What are the reactions at a journal bearing?
Well, it can move in the X direction, can't it?
Correct. And you guys, you have to look at each one isolated because of course, when there's three connections here, this thing can't go anywhere.
Mm-hmm.
All right. So you have to look at each connection separately. We're looking at the bar and this collar at A. And yes, you're correct, Mackenzie. It could move in the X and it could rotate in the X. So what are its reactions at supports? What can't it do?
At the Y and the Z.
Right. So it can't have an AY, or not say can't, it can't move. So it has an X, it has a Y, and an AY and AZ, and then it has moments, it resists moments, and we're drawing them in 3D. Remember we practiced that way back? My fingers to go in the direction of Y, and I'm drawing it in the positive. And I'm drawing it in the positive. And this is M, A, Z, and this is M, A, Y. Should I zoom in a little? Okay, what's happening, Marcine? What's happening at B? Maria, what's happening at B?
Is it a thrust bearing?
Read it. Read it.
I can't.
Oh, supports at A is a journal bearing, and the supports at B and C are ball bearings.
Oh, okay.
So what do I draw?
You draw a reaction in the Y.
A force or a moment?
A force.
Okay. Oh, sorry. Call it BY. And what else?
I think a ball bearing can tip, but it can't slide through, correct?
Right. Well, no, it can still slide this way.
Oh, okay, okay.
But there's another force that it can't do.
And the Z.
You mean here, right?
Uh-huh.
And that's
Oh,
X.
Yeah, ball bearing just has 2, right?
Yep.
Okay.
Okay, Matthew. What's going on at C? It also says it's a ball bearing. So what are the reactions at the ball bearing at C?
It would be the forces going up
Right,
with Z,
right, and
and the forces going with X,
right.
and that's it.
Great. Now, I have to remind you that this is really scrap. This is not my free body diagram. Myra, why is this not a free body diagram?
Because it's still showing connections.
Yes, awesome. Because it is still connected. I have to remove that bar from all the connections and draw all the reactions at the supports, and then it's a free body diagram. Okay, want to do another 3D one? We're up to Miles.
Quick question. With spheres and cylinders, you know how instead of marking distance, would we include radius or no?
Yeah, a radius or a diameter. Yeah, because you're going to need the distances, right? And typically you just need, well, either one, radius or diameter, but yeah. Okay, so now let's do this one, 26. Miles.
Miles planned to be absent today.
Okay. Peter.
Yes.
Okay, great. All right, so let me read it to you. It says the bar bracket, and the bar bracket is this thing. Here, here, here. The bar bracket shown in the figure, they want you to draw for everybody to. The support at B is a ball and socket joint, and the ends of the bar at A and C rest against smooth surfaces. Okay, so what do we want to draw at B? It's a ball and socket joint, like your arm.
We need a force in the X, Y, and Z direction.
Excellent. And remember, I'm drawing them parallel to the axes. Here's Y, here's X, and here is BZ. Good. And then Peter, it says that it's also the end of A and C. Oh, and we have to draw P, right? Because P is an external force there. And then it says A and C are resting against the smooth surface. So you have to figure out, well, what is the surface? This surface right here is a wall that's comprised of the XZ plane. And here's another wall of the YZ. So at A, how would I draw my force? Or what force would it be, first of all? Peter, I'll stay with you.
It would be a normal force.
A normal. And which direction is it going in? And remember, we're drawing a free body diagram of these 3 orange brackets together.
Right, so it should be going away from the wall. Or away
Right, so in the positive Y, right?
Correct.
So AY. And then what about at C?
At C, it'll be going in the positive X.
Excellent.
Away from the wall.
Oh, that's not A. Is there a point? Is that C?
Yes, that's
yes, C. Okay. Sorry. CX. And again, this is not a free body diagram until I draw the bracket away from this. So this is all scrap right now. Here. I have to draw the free body diagram. So this homework assignment's actually giving you practice to draw in 3D again, drawing complete free body diagrams now of whatever body they're asking you for. Let's look at another one.
Wait, I'm a little confused about the P in that last one.
Yeah, the what? The P?
yeah.
There was an external force on here, just pulling it.
Oh, okay.
It was already drawn. It's kind of like this one. See, there's a P1 and P2.
Uh-huh.
They're just external forces on here. So it's just something's applied there. We don't know what it is. I think we should do one with a collar, with a slot rather. Let's do this one. Let's draw a free body diagram of DEF. DEF. So Tim, we're up to you. What's going on at F?
We have it's resisting force in the X and in the Y.
Because it's what?
Because it's a pin.
Right. FY, FX. Okay, what's going on at D?
At D, we have a force P.
Right, we just have an external load of P applied. And now let's think about this. Again, for me, I don't like to memorize. I think about it instead. This is a 2D problem. Everybody's with me? Look up here. So it's a 2D problem. So a 2D problem we know can have I'm doing E. Could have a force in the X, could have a force in the Y, and it could have a moment about the Z. And what we're talking about here is the connection of this rod and this rod. This rod could move in here. So if you look at these two rods relative to each other, so if you had an erector set, you had a rod and another rod, and there was a slot in here, can these rods move relative to each other in this direction, Tim?
Yes.
Yes. So that means it does not resist it, so there's no reaction that way. What about in this direction? Can they resist motion in this direction?
They can resist motion.
They can. So
yeah.
Even though I started drawing out my force in the X and force in the Y, I could rotate my axes. And I know that they could move relative to each other this way. So there's really only a force going this way. And then what about, can they rotate in here? If this bar wasn't connected here, could it spin around?
I mean, it has...
You could take a look at your cheat sheet if you want. Look at a slot. It's called a pin and a smooth guide. Oh, and actually, this drawing isn't very good. Do you mind if I... You guys take a look at this. This is really a bar here that's solid. And this is a slot in here. So this is hollow in here. So it's a bar. Here's a bar and here's a bar. They're connected by it's kind of like a pin, but the pin can only slide in one direction. But it could still spin, right? So the only reactions at the support is a force perpendicular. So then the only other thing then is E. Let's just call it E. And I have to make sure that I'm putting in my directions of my forces. So in this case, you could choose to keep the XY axis in the regular direction, and then that would mean you have to find the components of E. Or you could rotate them and rotate these X and Y, but then you have to find the components of P. So either way, it's the same amount of work. I think we should stop here. So what you're going to be doing is you're going to be on engineering paper. You're going to draw a free body diagram of every single one of these. So you're going to get a lot of practice. Okay, and be sure to put axes and distances on them. Okay, I'm going to come back to you now. Okay, so now, couple of things. So one, my mom lives in New York, and I haven't seen her in a year, and my kids haven't seen her in a year, so we decided we're going to go visit her. We're going to battle COVID on the airplane. So hopefully we'll be fine, but it's important to see her. So I had to work around everyone's schedule. My kids are in school, I'm in school, and in the end, what I did is I made the flight on Thursday. I know that impacts you guys, but I made the video. I already made the video. It's already posted. So there's no in-class class on Thursday. So let me go to sharing the screen for a minute. Okay, so today's lecture, Tuesday the 13th, here's an overview, a summary of what we did. Here's all the schematics of the reactions it supports, the table that you completed on Friday, and then these are all the problems that you're doing, okay? So this file that we were working from today, who has given me a lot of grief, is also in homework 17. Because homework 17 is you're drawing free body diagrams of rigid bodies. Okay, let me move the pictures for a minute. Would you like me to post the solutions? I think you like to compare as you go along. So I'll publish the solutions. Okay. Then on Thursday, the topic we're doing is distributed loads. And it's really an expansion of equivalent systems. It's an expansion. It's just another level of doing force location problems. The announcement says no class today. It's a video lecture. Class notes and the homework, everything is posted. So I'm publishing this now. So again, there's an overview for distributed loads. There is a page of centroids and center of gravity. But once you go to the Zoom video, it'll cover all the stuff, okay? We're solving for distributed loads, not using integration, because in engineering, what we most want to be able to do is be able to figure out load distribution of composite distributed loads. So the recording that you have to watch is this one. But if you're intrigued and you want to see information about how to do integration, then here I added the integration. Actually, let me, I'm gonna change the wording of this. Distributed loads by integration. So this is the complete that you have to watch. And if you want to, you could add this. This is an extra piece. And then here's the distributed load homework. And actually it's mainly called distributed loads. So let me change it to, you could say distributed forces too, but let's just use the same terms always.
I just put October 12th.
And then
as the date.
Say that again.
Thursday is not the 12th.
Wait, no, I'm sorry. Hang on a second. And then I'm going to publish the solutions as well. Okay, what's your question?
It's a comment that Thursday is the 15th.
Thursday's the 15th, but the homework is not due until the 19th. So I'm not flipping the classroom. I'm running the classroom just like normal, where I teach it in the class, and then you do the homework, and the homework is due later. Instead, though, is you're going to watch a video of me on the 15th or before or after, and the homework is not due until the 19th.
Okay, yeah, but just for, the sake of avoiding confusion, your title is Thursday, October 12th. Thursday.
I
is
see
the
what you're
15th.
at. I see what you're saying.
It's because you probably recorded it on the 12th.
Right, so that's why. Yeah, sorry. Okay, so it's a 15th. Thank you. I didn't understand what you were asking me. Thanks. Great. All right, does everybody get it? So I'm still in office hours every day when I'm there, and I'm going to be teaching from there. It's going to be the same thing. The only thing is this Thursday, no office hours, no class. Okay. All right. And then again, people have said that the calendar has been helpful for them. The calendar shows when everything is due. So keep your eye on the calendar. It's showing when everything's due. Okay, and now I'm going to stop sharing, and now I need to find out from you when I should open this quiz that we were going to take in class, and now you're taking it outside of class. I know some of you are available now, and some of you are not, right? Is physics going on today synchronous?
Yes.
Yes. Okay, so then when can those of you in but some of you want to take it right now, right? Yes. Yeah. Okay, so it's going to open soon. And then, but when of the rest of you can you take it? Could I open it now at 11 and keep it open until until 3, or is that a problem?
That's a lot of us have 4B lab right now.
Okay, and when does 4B lab end, at 2:30?
Honestly, I have no idea.
When does it usually end? It's supposed to be 3 hours.
It ends in I think an hour and a half at the most.
Okay.
It ends at 12:30.
Ends at 12:30. Okay, so if I do 11 to 3, that should be okay for everybody? Is it a problem for anyone? 11 to 3, is there a problem for anyone? No. Okay, I'm going to go open it now. It's actually a relatively short quiz. Okay. Okay, you're free to leave. I just give me 5 minutes or so to get all this, the times changed.
Okay, thanks, Joanne. Travel safe.
Okay, thank you.
Thanks, Joanne.
Yeah, see you guys.
Yeah, be wary of your destination too, not just the ride, not just the travel.
Yep. Well, we have a quarantine, so hang on, let me get this done first.
All right, thanks for your hard work.
Okay, see ya. 13.
Joanne, you're going to have to introduce us to your mom when you're out there.
Okay. Okay, I will. Thanks. Right, yeah, she's 85, and I mean, it's better to go see her.
No, totally.
And it's a surprise. She doesn't know I'm coming. We're coming.
Oh, cool. Have a good trip, Joanne.
Yeah, thank you. Okay, so I just made it. It's open now, and it closes at 3.
Thanks, Joanne.
Yeah, you're welcome.
Thank you.
Okay.
Oh, and I'm by mistake been the host this whole time.
Yeah, you have been. I made you the host when I got off, otherwise everybody would get knocked off.
Here you go.
What does that mean, though?
That I can end the meeting for everyone.
Oh, okay.
And stop the recording.
All right, so can you make me the host now or no?
There you go. Yeah.
Okay, great. Thank you.
Of course.
Okay.
Safe travels, Joanne.
Okay, thank you. Okay. Hey, Tony.
Hey, how's it going?
Hey, how are you? I never got to you. You'll have to start next time.
Yeah, yeah, I noticed that. I was like the last one.
Yeah, Tim, I didn't get to you or Victoria.
Yeah.
So, how are you doing? How was today?
Today was good. I was able to follow along just fine. Nothing too hard.
Okay, not
All right.
confusing.
No, it was all pretty clear.
It seemed like it started. Could you let me know how the Friday labs are going? Just your honest opinion, and it's confidential. Oh, wait.
Oh, recording. Yeah.